Adding constraints part 1, the floor. Our point right now will keep falling forever basically. We need to figure out a way to tell Blender, hey Blender, once the point reaches the floor, make it bounce off of it. This will be a fun exercise. The first question that comes to mind is, when does the point reach the floor? The answer is simple, once the position of the point is equal or below 0. So now, if I go back to this sentence, hey Blender, once our point reaches the floor, we want it to bounce off of it, we can change it to the following sentence. Hey Blender, once the position of our point is equal or less than 0, we want to bounce off the floor. Now comes the second part. How can we make it bounce off the floor? The easiest solution will be to reverse all the forces that are applied on our point, or on our ball. Right now our simulation is making the point fall down, so all we need to do is to tell Blender that once the point hits the floor, reverse the simulation. In other words, reverse the velocity and position. To fully understand that, I want to explain the architecture of our simulation engine. We first define the acceleration, which we use to define the velocity, which we use to update the position. It's a pretty systematic or algorithmic in a sense. It's a step-by-step process. Now we will tell Blender, if the position of the point is less than 0, reverse the velocity and reverse the position of the point. This will lead to the point bouncing up. It's like we're building a mini engine that will kick in once the position of the point is less than 0. So let's translate all of these thoughts into nodes. The first step in building our mini engine is to know when will this engine kick in. I said that multiple times, when the position of the point is less than 0. I'll start by adding a position node, which will give us the position of the point. Then I'll add a node called a separate XYZ, because we only need the position on the Z-axis, since it is the one responsible for defining the position of the point up and down. Add a compare node and set it to less than 0, and this is our condition. One way to read the logic of these nodes we created is the following. When the position on the Z-axis is less than 0, do something. Now we will build what should happen when this condition is true. This should be simple, because all we need to do is to run the same engine we built, just in reverse, which we can do easily by multiplying it by -1. So first we need to reverse the velocity. The point used to go down, now it needs to go up. How can we update the velocity? Easy. Add a store named attribute, change the type to vector, and we need velocity. Whatever we will write here now will override the values we had previously for the velocity vector. I'll then add a named attribute, vector, velocity. This will give me the velocity value from the previous frame, and I will multiply it by -1 on the Z-axis and 1 on the X and Y axes, since I don't want them to change, because multiplying by 1 will always lead to the same result. And I will plug that into the value socket of the store named attribute. Now we reverse the velocity vector. Let's move to updating the position so the ball goes in the reverse direction. I'll add a set position node, add a position node, add a vector math and multiply it by -1 on the Z-axis and 1 on the X and Y axes, and plug that straight into the position, because we want to straight up change the position, not just the offset. And now, this is our mini engine responsible for reversing the simulation if the point goes below 0. But right now, Blender still doesn't know when to run this small engine, because we need to plug our nodes defining the condition into the selection socket of the store named attribute and the set position. So now, both of these two operations of changing the velocity and changing the position will only run once this condition is met. If I hit play now, notice what will happen. Our point is bouncing, and that's how we can introduce constraints to our simulation. The ball now will bounce forever, but in real life it should lose energy slowly until it stops. A way around that will be to tell Blender to decrease the velocity gradually. You can do that by increasing the velocity vector, so instead of multiplying it by -1, which is a perfect reflection, you multiply it by -0.8 for example. Now the simulation will lose steam slowly whenever it touches the floor, until it stops. The way we programmed friction right now only applies once this condition is met, once the ball touches the floor. But in real life, the ball should actually lose speed gradually from the beginning of the simulation. A way around that is to add a vector math node, set it to scale, and plug it right before the store named attribute defining the velocity, and set the value to something like 0.98. Now the simulation will lose energy overall, or at every frame. Why? Because as we know, Blender compiles the simulation every frame. For our simulation, I'm going to delete the scale node and I will program friction from the nodes responsible for the constraints in a future video. Now we build the constraint system for the floor. We also need to build some constraints for the side walls, and that's exactly what we will be doing in the next video.